if we have a mass m subject to net restoring force F net equals negative kx, where x is measured relative to some position, which will be the equilibrium position, then it follows from what we've seen previously that x of t equals a cosine of omega t plus phi. Okay, where omega is the square root of k over m. Now this comes from the differential equation that we've talked about a couple of times. This solution is rather straightforward. If you write out the differential equation, consider what the second derivative of the position is equal to. Second derivative of the position being the acceleration, F net being mass times acceleration, etc. And review that if necessary. Once we know this, and we can invoke the circular model, we can find the velocity and acceleration in a very straightforward manner by taking a couple of derivatives. Okay? Then, what do we get? Well, what's the kinetic energy as a function of t? We know the velocity is a function of t, the acceleration as a function of t, and the position as a function of t. What is the kinetic energy as a function of t? Well, kinetic energy is 1/2 mv squared. V, of course, is your v of t. Okay, whatever v of t is, kinetic energy is 1/2 m times the square of that quantity. And v of t is this, so we simply substitute this expression for v of t, and we find that the kinetic energy is this. And I don't have to read it to you, you can see it there. Okay, then, what's the potential energy function? Well, potential energy is the work done by a conservative force from one position to another position. Now, in this case, the first position is your reference position. For a force of this nature, we're going to use as reference position the x equals 0 position where the force is, net force is 0. Okay? So that that's going to be equal then to the negative of the integral from 0 to x, and the 0 there and the x from the other integral are kind of interfering with one another. Don't have a good piece of chalk, but I'll use this one. Okay, well, let's see, this x here is is a limit on this integral. It's the same limits as on this integral. Okay, anyhow, so we integrate the force with respect to x. That's how we calculate work. Okay, we integrate force with respect to x. Since we're doing the work done by conservative force, we integrate the conservative force with respect to x to get our potential energy relative to position 0. So I maybe should make a note here. This is potential energy relative to the x equals 0 position. Okay, it's going to be the integral of your conservative force. Well, I'll say why in a minute, but this is a conservative force because it's path independent, but we'll discuss that shortly. Okay? So right there's your force. That's what's integrated with respect to x from 0 to x. And the potential energy at x then is going to be equal and opposite to the integral done by the conservative force. Okay? And that comes out 1/2 kx squared. Now, what do I mean by conservative force? What am I talking about when I talk about path independence? Well, let me give you an example of something that isn't path independent. Here's a chunk of chalk. I'm going to talk about the frictional force on this chalk. Okay, now my position, let's say my domain is every position from this, from this side of the screen to that side of the screen. So, if I want my potential energy change between here and here, I would have to calculate the frictional force exerted on this thing as it moves from here to here. Now I'd have to integrate the frictional force. Although the force is probably constant, let's treat it as if it's constant. I multiply the frictional force by the displacement. Well, the frictional force in this case is in this direction, right? At every position between here and here, the frictional force is in this direction. Okay? Okay, well, Now I want to calculate the potential energy change as I move back. But as I move back, the frictional force is in that direction. Frictional force at any point, here, let's just take this point. The frictional force at this point was in this direction when the chalk moved that way. Now it's in this direction when the chalk moves this way. Well, that's not path independent. The path, if the path is from here to here, then the frictional force at this point is to the left of the screen. If I move from here to here, when I get to this point, the frictional force is to the right of the screen. That's not path independent. This, however, is path independent. There's no dependence on my direction of motion. It's at this point along the line. This is the force no matter what else is happening. Okay, so that's path independent and therefore conservative. Now, it follows then that this is the change in the, or this is the potential energy. It's the change in potential energy between the 0 position and the x position, okay? And that is the potential energy then relative to the 0 position, and that's how I'm going to define this. Okay, well, okay. Now what's potential energy as a function of t? Okay, well, let's see. Potential energy as a function of x is 1/2 kx squared. For this oscillator, x of t is this. So if this is an oscillator, amplitude A and so forth, I just substitute that expression for x of t and I get this. Okay? Now of course I could square this. I'd get an a squared cosine squared of omega t plus phi. So I'd have 1/2 k a squared, etc. times the cosine of omega t plus phi. Squared cosine omega t plus phi. Okay? Well, now the total energy is potential energy plus kinetic energy. That's what we mean by total mechanical energy. I didn't write the word mechanical. I probably should have, but I didn't. Well, when? Do you want the potential energy at time t, or do you want the total energy at time t, or the total energy at position x? You can do it either way. Well, we have the expression for potential energy at time t here, and we have the kinetic energy at time t here. So we might as well do this at time t. So at time t, total energy is this plus this, so we just write down this expression, and I did square inside the parentheses. You got the a squared, cosine squared, and so forth, and this expression. Okay, we just write them down. Okay? We don't have to interpret them at this point, but we do have to get used to what they're telling us as we move along. Okay? Okay, but there's the expression for the total energy, but maybe we can simplify this, okay? So let's see, what do we know? Well, we know that omega is the square root of k over m, so we could substitute that here. And that might be helpful because this involves k and this expression doesn't. Okay? Well, we replace omega with square root of k over m, then omega squared is going to be k over m. So this expression is the same as this expression. The only difference being I've replaced omega squared by k over m. This expression hasn't changed. Of course, now if I multiply m times k over m, I just get k. And look at what I've got then. What am I left with? I'm left with 1/2 k a squared times the sine squared of omega t plus pi. And that matches the coefficient of cosine squared of omega t plus pi that I have up here. So I can factor out a 1/2 k a squared, and I'm left with cosine squared of omega t plus pi plus sine squared of omega t plus pi. Well, what's really neat about this, of course, is we know it's the Pythagorean identity. The cosine squared of some quantity plus the sine squared of the same quantity is equal to 1. Just the basic definition of the cosine and the sine function in terms of the circular function, if you like. And you have your circular, you have your unit circle, and you have some angle here. Well, this leg of the triangle is your cosine. I'm writing this small. This leg of your triangle is your sine, and that's the cosine and the sine of whatever this angular position is. And the hypotenuse is 1. Well, then by the Pythagorean theorem, this squared plus this squared equals this squared. So that the cosine squared plus the sine squared is 1 squared, which is just 1, as long as you have the same angle here, okay? So, you know, we just invoke all that, and this simplifies to 1/2 Ka squared, and this is an expression for your total energy. Okay, well, then we ask, okay, what's the maximum value of the potential energy, okay? Well, I'm going to go back to the potential energy as a function of x, 1/2 kx squared, because, of course, if this thing is moving, oscillating with amplitude A, you can visualize that as the point moving around the reference circle on a circle of radius A. The excuse me, x projection of this point moves then, well, if we're moving around this way, if we happen to start here, we're going to move over here, back here, over here, back here, as the point moves around and around the circle. So that the maximum value of x is A, and it also has a minimum value of negative A. Okay, so the potential energy is 1/2 kx squared. X goes from negative A to A, so the maximum potential energy is what you get if you put the maximum magnitude of x into this function. So you put A in, you get 1/2 Ka squared. Also, if you put negative A in, you're squaring it, you still get 1/2 Ka squared. Okay? So potential energy is 1/2 Ka squared. This is the max. Okay? Now, we could also see what the max is by looking at this expression, 1/2 K times A cosine and quantity omega t plus phi squared. And then the whole quantity, A cosine. All of this is squared. I don't think I said that right. Okay? What can you tell me about the maximum possible value of this quantity? Well, the cosine, we got smudged out here. My cosine just kind of got disappeared, which is too bad because I took a lot of trouble to write that this close to the ledge. Okay? The cosine of omega t plus phi takes every value from -1 to 1 as you move around the circle. Okay? The cosine goes from -1 to 1. Okay, here's your unit circle. Cosine can be as big as -1, as small as big as 1, as okay. It's between -1 and 1. I'm not going to get that sentence to come out. Okay? What's going to be the maximum value of the squared cosine? Well, it's going to be 1. Okay? It's going to be 1 if the cosine is 1. It's going to be 1 if the cosine is -1. So here and here. And of course, those are the points where x equals A and negative A that we got up here. The cosine is going to be 1, and this is going to come out 1/2 Ka squared. Okay, 1/2 Ka squared cosine squared omega t plus 1. That takes the maximum value, 1/2 Ka squared, when the cosine is plus or minus 1. Okay, now there's a whole lot of information here, a lot of stuff to understand. And we're going to build on it just a little bit next.